Hello people, welcome to in this concluding part 3 of resistors in series lecture. We'll try to find out the net, or we can say total or equivalent resistance of this series combination. Consider this electric circuit, this one, consisting of three resistors R1, R2, R3, and they are connected in series with each other. So it is a series combination of three resistors connected between 2 points A and B, along with a battery of V volt, a plug key, and an ammeter. Let I be the current flowing through this circuit. So from our lecture 1, we know that the current through each resistor, whether it is R1, R2 or R3, the current will be same, that is it will be equal to I. So I current will flow through R1, R2 and R3. Let the potential difference across resistor R1 be V1, across R2 be V2 and across R3 be V3. So I am denoting this as the potential difference across R1 as potential difference VXP, which is V1, VQS be V2 and VTY is equal to V3. I have measured these potential differences with the help of a voltmeter. Also, let the potential difference between points A and B, that is across this series combination of three resistors VAB, this one and this one, these 2 points, let it be V. So VAB is equal to V. Now from the discussions in previous lecture, we know that VAB is equal to VXP plus VQS plus VTY. On substituting values, I will get V is equal to V1 plus V2 plus V3. Let us call this equation 1. Now our task is to replace this series combination of three resistors with a single resistor RS and form a new circuit like this. But the condition is that the current in the circuit should remain I after the replacement. That is, in this circuit before replacement the current was I, and even after replacement the current in the new circuit should also be I. Now here one thing has to be noted, that we have connected the same battery. We have not replaced the battery, we have only replaced this RS with this parallel series combination of three resistors. So we can call it a equivalent resistance. Why? Because even after replacing this resistance, the current in the circuit has not changed. Now I am going to apply Ohm's law to each individual resistance of this circuit as well as to the resistance of this circuit. So for this one R1, if I apply Ohm's law here, then in this case V1 will be equal to I into R1. Why? Because I is the current flowing through this R1. Again for R2, V2 will be equal to I into R2 and V3 will be equal to I into R3. Whereas for this equivalent resistance, the current flowing through the circuit is I and the resistance is RS. So in this case, since the potential difference between these 2 points is V, So I can write through Ohm's law V is equal to IRS. Now this is a second equation for me, and now what I am going to do, I am going to replace these values V1, V2, V3 in this equation with the corresponding values IR1, IR2 and IR3, and I will substitute this IRS value also in this equation 1. So now we will have a new equality like this. We had this relation V is equal to V1 plus V2 plus V3, and as we saw that V was equal to IRS and the value of V1 was IR1, value of V2 was IR2 and value of V3 was IR3. So on further solving this equality, IRS will be equal to I taken as common R1 plus R2 plus R3, and on cancelling out Rs, that is the equivalent resistance, the value of equivalent resistance will be equal to R1 plus R2 plus R3. So it means that whenever a number of resistors are connected in a series combination, then the net resistance of the circuit, this is the net resistance. So the net resistance of the circuit is equal to the sum of all the individual resistors that are part of the series combination. So if there have been more than 3 resistors in series, then let's say 4 and 5 resistors were also there. So I would have written Rs will equal to R1 plus R2 plus R3 plus R4 plus R5. So from this relation for series combination, we can conclude that first, when several resistors are joined in series, the total resistance of the series combination equals the sum of their individual resistances. This is the first conclusion from this whole discussion. Second conclusion is the resistance of the combination Rs is greater than any individual resistance R1, R2, R3 present in the circuit. That is, R is greater than R1, Rs is greater than R2, and Rs is greater than R3. This can be well understood with the help of a following example. For example, if suppose that this resistance R1 had a value of 1 ohm, this had a value of 3 ohm, and this had a value of 6 ohm, then the total value of this will be 10 ohm. So it means that the net equivalent resistance of the circuit will be 10 ohm, and we can easily see that 10 ohm is greater than 1 ohm, 10 ohm is greater than 3 ohm, and 10 ohm is greater than 6 ohm. So this is the meaning of this second conclusion. So while solving any problem pertaining to series combination, these two conclusions have to be kept in mind. If you have query regarding this lecture, please comment. Thank you.